Is time travel possible?
We can definitely travel into the future by moving faster relative to everybody else.
Ever thought about what it would be like to hop through time? Going back to relive your favorite moments or forward to see what amazing things the future holds? Well, a breakthrough at Cambridge University just a few months ago has brought us closer to turning this fantasy into reality. Scientists have cracked the code, and the first successful time travel experiment has been conducted.
Let's say I'll call the spin up a 1, and I'll call spin down a 0.
In this mind-boggling exploration, we'll unravel the mysteries behind time travel, explore the ingenious process devised by these scientists, and delve into the potential implications. Join us as we uncover the details of the first successful time travel experiment that could change everything we know. The evolution of time travel concepts. Time travel, a fascinating idea, has captured people's imagination for a very long time. The mere idea of journeying backwards or forward in time to witness historical moments, rectify past errors, or catch a glimpse of the future has entranced minds throughout various cultures and historical periods. This concept didn't emerge overnight. It has lingered in myths, legends, and philosophical discussions long before scientific investigation took root. Over time, it evolved into one of the most compelling themes in literature, cinema, and scientific inquiries, unveiling a rich fabric of scientific and philosophical complexities. The concept of time travel isn't just about hopping across different points in time. It's about transcending the linear flow of past, present, and future as we perceive them in our daily lives. Although often relegated to the realm of science fiction, theoretical physicists have delved into the possibility of time travel within the confines of established scientific principles. The roots of time travel trace back to ancient Greek mythology. Tales of figures like Kronos and the Moirai, possessing the ability to manipulate time, reflect humanity's enduring fascination with the passage of time and the tantalizing prospect of surpassing its boundaries. These mythological accounts serve as a testament to the profound interest humans have held in time's nature and our potential to transcend its limitations. In the 18th century, the British philosopher John Locke delved into the philosophical implications of time travel within his work, an essay concerning human understanding. He contemplated the concept of personal identity across time and pondered the paradoxes that altering the past might trigger. Expanding on the scientific aspects, contemporary explorations of time travel are rooted in theoretical physics. Concepts such as wormholes, time dilation, and the theory of relativity are often central to discussions on the plausibility of traversing through time. Wormholes, hypothetical tunnels through spacetime, present a potential shortcut for accessing different temporal points, while time dilation, a consequence of high speeds or strong gravitational fields, allows for the relative passage of time. Albert Einstein's theory of relativity, particularly the notion of time being relative and not absolute, has spurred inquiries into the practicality of time travel within the bounds of physics. Moreover, scientific inquiry into time travel extends beyond theory. Experimental endeavors, though in their infancy, have probed the manipulation of time on a minuscule scale. Studies on particles and atomic clocks have demonstrated minuscule time distortions, laying a foundation for future advancements. In the realm of popular culture, time travel has become a staple theme, fueling countless narratives in literature and cinema. From H.G. Wells' The Time Machine to the iconic Back to the Future film series, imaginative explorations of time travel have enthralled audiences, fostering a collective fascination with the concept. Theoretical frontiers in modern physics. The emergence of modern physics in the 20th century injected a new dimension into the exploration of time travel. Scientists, armed with evolving theoretical frameworks, embarked on a quest to unravel the potential for traversing time. However, diving into the realm of time travel plunges us into the depths of complex theoretical physics. Key among these theoretical frameworks is Einstein's theory of relativity, which revolutionized our understanding of space-time, the interconnected fabric of space and time. This theory serves as a cornerstone in contemplating the plausibility of time travel. Within these conceptual landscapes, scientists have contemplated intriguing possibilities such as wormholes, black holes, and closed time-like curves, envisioning them as potential gateways to navigate through temporal dimensions. Wormholes, hypothetical tunnels connecting different points in space and time, have captured the imagination as potential shortcuts for traversing vast temporal distances. Black holes, immensely dense objects with gravitational forces so intense that not even light can escape, harbor theoretical potential as portals or conduits to manipulate time. Closed time-like curves, theoretical paths in space-time that loop back on themselves, offer tantalizing prospects for temporal journeys. However, while these theories spark curiosity, they also face formidable challenges. The famed grandfather paradox encapsulates one such hurdle, illustrating the paradoxical conundrum of altering the past. Consider, if someone were to travel back in time and prevent their grandparents from meeting, thus preventing their birth, a paradox arises. This paradox highlights the complexities and contradictions inherent in changing past events, leading to logical inconsistencies. Causality, the fundamental principle that an event is preceded by a cause, poses another intricate challenge. Altering past events could create ripple effects, disrupting the chain of causation and leading to unforeseen consequences. The interwoven nature of cause and effect complicates the notion of altering the past without inducing paradoxes or logical inconsistencies. The exploration of time travel within the framework of theoretical physics is an exercise in navigating these complexities. Scientists grapple not only with the technical aspects of manipulating space-time, but also with the philosophical implications and logical quandaries that arise from the prospect of altering the past. As intriguing as these concepts are, their practical realization remains elusive. Theoretical frameworks provide avenues for contemplation and hypothesis, but lack empirical confirmation. They dwell in the realm of mathematical equations and theoretical models, awaiting the day when technology and understanding converge to unveil the mysteries of time. In 1915, Albert Einstein changed the game with his theory of general relativity, which completely shook up how we think about gravity and space-time. One major idea that came out of this theory is the concept of closed time-like curves, CTCs. These are like hypothetical paths in space-time that, if they existed, would allow something to loop back to its past. The thing is, though, these CTCs are still up in the air when it comes to whether they exist. But despite the ongoing debate, they've become a cornerstone of discussions about time travel. One idea suggests that if you could get something massive spinning super fast near the speed of light, it might create a kind of tunnel through space-time. Picture it like a whirlpool pulling something back to an earlier point in time. Then there's the notion of wormholes, which are like these theoretical tunnels connecting far-off points in space-time. Physicist John Wheeler first came up with this idea. If these wormholes were real, they could open up travel between different parts of the universe or even different moments in time. But wait, there's more. Now toss quantum mechanics into the mix. Quantum entanglement is this super odd thing where two or more particles get linked up in a way that their fates are intertwined, no matter how far apart they are. This whole new science has sparked ideas about manipulating information, and maybe even nudging events in the past. Imagine using these entangled particles to send information back in time. You take one half of an entangled pair and shoot it into one of those hypothetical CTCs. Then, somehow, it might interact with its other half in the present, effectively sending a message back in time. This idea is like trying to change the past by working with entangled particles. Another idea using quantum entanglement is to tweak the state of particles in the past. By taking advantage of the connections between entangled particles, the thinking goes that maybe we could go back and fiddle with how things turned out. Challenges to time manipulation. While the concept of time travel is undeniably exciting, it remains firmly rooted in intense debate and speculation. The theoretical approaches proposed so far, though captivating, face significant challenges and limitations that temper the allure of exploring the past or future. One major hurdle in the pursuit of time travel is the potential violation of causality, a fundamental principle asserting that effects cannot precede their causes. If time travel were achievable, The ability to alter events in the past could disrupt the established order of cause and effect, leading to paradoxes and logical inconsistencies. Another formidable challenge arises from the astronomical energy requirements associated with manipulating space-time or creating wormholes. The immense amounts of energy needed far surpass the capabilities of current technology. The practicality of harnessing such colossal energy remains a significant roadblock, hindering the realization of these theoretical concepts. Moreover, the stability and viability of wormholes, those hypothetical tunnels connecting distant points in space-time, are shrouded in uncertainty. The looming possibility of their collapse poses a real risk, potentially trapping time-traveling individuals inside, adding an element of danger to the envisioned exploration of temporal realms. Beyond the scientific challenges, time travel raises profound philosophical questions about the nature of reality, free will, and the very fabric of the universe. The prospect of altering past events or influencing future outcomes forces us to confront intricate debates about determinism and free will. If time travel were indeed possible, a pivotal question emerges. Would changes to the past generate new timelines, branching off from the original? Or would these alterations ripple through history, influencing the present and future? These philosophical quandaries ignite discussions about the nature of causation and the malleability of existence, challenging our understanding of the fixed order of events. Time travel isn't just a scientific puzzle, it brings forth ethical dilemmas as well. The ability to change past events might seem thrilling, but it raises concerns about unintended consequences or disruptions to the natural flow of history. These considerations prompt important ethical questions about the responsibilities and repercussions of altering what has already occurred. The weight of these ethical considerations adds complexity to the already daunting challenges and limitations associated with time travel. Yet despite these hurdles, the pursuit of understanding time manipulation persists. Scientists continuously push the boundaries of our comprehension of physics and the universe. The exploration of time travel serves as a frontier that compels scientists to seek new theoretical frameworks and technological advancements. These innovations are aimed at overcoming the obstacles that currently limit our ability to traverse time. Quantum entanglement and retroactive changes. The study of time travel, whether it remains theoretical or becomes a reality, holds immense value for us. It's not just about futuristic gadgets. It forces us to grapple with big questions about time itself and how events are linked in the universe. Time travel isn't just about visiting the past or the future. It challenges our understanding of cause and effect, reality, and our place in the cosmos. Scientists have been tirelessly working on finding a theoretical framework for time travel. Recently, they made progress by delving into quantum entanglement. This study allowed them to simulate a way to travel backwards in time, altering an event after it occurred, successfully achieving this in about 1 out of every 4 attempts. However, it's crucial to note that the Cambridge University team clarifies they haven't crafted a time machine. They're emphasizing that their process adheres to the laws of physics, even while seemingly changing events after they've already happened. David Arvidson Shukur, the lead author from the Cambridge Hitachi Laboratory, simplifies this complex concept with a relatable example. Imagine sending a gift to someone. You need to send it on day 1 to ensure it arrives by day 3. However, you only receive the person's wish list on day 2. In this scenario, sticking to the recipient's timeline means sending the gift on day 1 without knowing their preferences. As Arvidson Shukur points out, this might result in the gift being late or not what the person wants. However, he proposes an intriguing idea. Imagine being able to change what you sent on day 1 using the information from the wish list received on day 2. This possibility parallels what the researchers claim can occur in certain circumstances. Their simulation, rooted in manipulating quantum entanglement, demonstrates how one could retroactively modify past actions to ensure the desired outcome. Quantum entanglement, a phenomenon where particles become interconnected regardless of distance, plays a central role here. Manipulating these entangled particles could potentially enable a form of retroactive action, allowing individuals to adjust past decisions based on future information. The significance of this research extends beyond the scope of sci-fi fantasies. It challenges our fundamental concepts of time's linearity and causality. While this simulation doesn't equate to a practical time machine, it signifies a significant step forward in understanding the intricacies of quantum mechanics and its potential implications for altering past events. The scientists' caution is essential. The current research remains within the realm of simulation and theory. Practical applications of backward time travel are still far from realization. However, these findings open new avenues for exploration, not just in the realm of time travel, but also in comprehending the deeper fabric of our universe and the possibilities hidden within quantum mechanics. Insights from simulated time travel. The Cambridge research team delved into the realm of quantum entanglement, a phenomenon where two particles become deeply connected, regardless of the distance between them. Their simulations, detailed in the journal Physical Review Letters, recreated the entanglement of two particles. In this setup, one particle was sent off for use in an experiment. The groundbreaking aspect emerged after the completion of the experiment. The researchers gained new insights that could have altered their actions during the experiment. Nicole Younger-Halper, a co-author of the study from the National Institute of Standards and Technology and the University of Maryland, elucidated that the manipulation of the second particle by the experimentalist effectively influenced the past state of the first particle. This manipulation resulted in a change in the experiment's outcome. In essence, by altering the remaining particle, the researchers seemingly altered the past, albeit within their simulations. The researchers coined this effect as remarkable. Yet there was a significant caveat. The experiment altered the past only 25% of the time. This translates to a 3 in 4 chance of failure, as indicated by Arvidsson Shakur. In simpler terms, 1 out of 4 attempts at altering the past yielded the desired outcome. For instance, if the desired gift was a pair of trousers, there remained a possibility of receiving the wrong size, color, or an entirely different item like a jacket. However, despite this limitation, the researchers found a silver lining. They could detect when the attempt failed in their simulations. This awareness allowed them to rework the system to potentially achieve the backward time travel effect they desired. To overcome the odds, they proposed the use of a filter, a theoretical tool enabling the experimenter to send multiple solutions and discard the undesired 75%. Aidan McConnell, a co-author who conducted this research during his master's at the Cavendish Laboratory in Cambridge, offered a simplified analogy. Imagine sending multiple parcels on day 1 and by day 2, knowing which parcel should have been sent. When the parcels arrive on day 3, 1 in every 4 deliveries matches the intended gift. The recipient is instructed to discard the unwanted deliveries, effectively selecting the correct one. This analogy mirrored the researchers' proposed approach of discarding undesired outcomes to achieve the desired result. However, it's important to note that these groundbreaking findings were confined to simulations. While successful, these simulations were based on known behaviors of entangled particles. Despite demonstrating a method to potentially alter experimental outcomes in the past 25% of the time, the researchers emphasized that this form of backward time travel shouldn't be likened to what's portrayed in movies or comic books. The scale and control seen in those fictional portrayals remain far beyond the realm of current scientific achievement. Arvidsson Shakur clarifies that their research doesn't propose a mechanism for time travel, but rather delves deeply into the core principles of quantum mechanics. These simulations don't enable individuals to journey back and alter their pasts. Instead, they offer a means to rectify past issues in the pursuit of a better tomorrow. Shakur emphasizes that while these simulations can't change personal histories, they may help address past problems, allowing for a more promising future. He points out that the failure rate of their backward time travel system is somewhat reassuring, especially for physicists reliant on Einstein's theories of relativity and the scientific frameworks built upon them. Shakur finds solace in the fact that the proposed system requires a filter to function effectively. He notes, "The world would be very strange if our time travel simulation worked every time. Relativity and all the theories that form our understanding of the universe would be thrown into uncertainty." The need for a filter, according to Shukur, aligns with the expected behavior based on established scientific principles. To comprehend the implications of the experiment, familiarity with certain terms becomes crucial. Quantum entanglement, for instance, refers to the interconnectedness between particles, regardless of distance. CTCs represent theoretical paths through spacetime that loop back onto themselves, suggesting potential time travel routes. Wormholes are speculative features of spacetime that could serve as shortcuts connecting distant points, hypothetically enabling traversal through space and time. Understanding these terms aids in grasping the complexities and potential implications of the experiment. The experiment itself probes the boundaries of our understanding of quantum mechanics, time, and the interconnectedness of particles, without directly defying established theories like Einstein's relativity. Navigating wave-particle duality and entanglement. Quantum physics delves into the study of the tiniest building blocks of our universe, matter and energy, operating at levels unseen by the naked eye, the atomic and subatomic realms. Here, particles behave in ways that seem almost magical, defying the predictable laws that govern our everyday, larger-scale world described by classical physics. Particles exist in multiple states at once, blurring the lines between what we understand as solid, liquid, or gas. This phenomenon challenges the traditional rules of physics, where an object can only be in one place or state at any given time. This bizarre behavior is part of what's known as quantum superposition. Moreover, these particles showcase what's called the wave-particle duality. Imagine a particle behaving both as a wave and a tiny localized object at the same time. It's akin to observing a coin spinning in the air, uncertain whether it's showing heads or tails until it lands and you catch a glimpse. This perplexing behavior remains a cornerstone of quantum physics. One of the most mind-boggling aspects of this quantum world is entanglement. When particles become entangled, it's as if they form an inseparable bond, regardless of the distance separating them. Imagine two friends sharing a magical connection. What happens to one friend instantly affects the other, no matter how far they drift apart. Even more astonishing is that measuring the state of one entangled particle reveals the state of its partner instantaneously. It's like having a pair of synchronized watches. Adjusting one instantly adjusts the other, regardless of the distance between them. This instant communication between entangled particles seems to defy our understanding of how information can travel through space and time. Scientists have speculated that this phenomenon might hold the key to challenging our notions of time travel. The instantaneous connection between entangled particles appears to surpass the constraints of both space and time, hinting at possibilities that push the boundaries of our current understanding of the universe. In experiments, particles have been entangled and then separated by great distances. Yet, when one particle's state is altered, the other responds simultaneously, as if the distance between them is inconsequential. This curious behavior has led scientists to explore its potential applications in various fields, from ultra-secure communication networks to advanced computing systems. The tantalizing prospect of manipulating these entangled particles for communication or computation has ignited a spark of excitement among researchers. The ability to harness this phenomenon could revolutionize technology and transform how we approach communication, cryptography, and information processing. However, while the potential applications of quantum entanglement are vast and thrilling, harnessing this phenomenon for practical purposes remains a formidable challenge. The delicate nature of entangled particles makes them susceptible to interference from their surrounding environment, posing significant hurdles in maintaining their entangled state over extended periods. Now it's time for today's subscriber pick. Recent evidence from the realm of theoretical physics indicates the first successful time travel experiment has been conducted. Scientists have been actively exploring the theoretical possibility of time travel, making strides by leveraging quantum entanglement. Their recent study, not about creating a time machine, but exploring the principles of physics, simulated a method to potentially alter events after they've happened, successfully achieving this around 25% of the time. The team emphasizes that while this doesn't equate to a practical time machine, It challenges our understanding of time and causality. Using a relatable analogy of sending a gift without knowing the recipient's preferences, they illustrate how their simulation involves retroactively adjusting past actions based on future information. This manipulation is rooted in controlling entangled particles, which exhibit a connection regardless of distance. In their experiments detailed in physical review letters, scientists manipulated one particle to influence the past state of another, seemingly altering the past's outcome. This manipulation succeeded in about 1 out of 4 attempts. They proposed using a filter, like sending multiple parcels, and discarding undesired outcomes to potentially improve success rates. However, it's vital to note that these breakthroughs remain theoretical and simulation-based. They don't offer practical time travel, but hint at the potential to rectify past issues based on future insights. The study delves into quantum mechanics' core principles without enabling individuals to journey back and change personal histories. The need for a filter aligns with established scientific principles, reassuring physicists grounded in relativity theories. Let us know what you think about these recent experiments. Theoretical perspectives on entanglement and the past. The notion of physically journeying through time remains a subject that sparks debate and speculation, often residing in the realm of theory rather than practicality. However, within the captivating world of quantum entanglement, a theoretical framework emerges, one that potentially allows the manipulation of information and events in the past. At the core of this theoretical framework lies the phenomenon of instantaneous communication through entanglement, seemingly defying the limitations imposed by the speed of light. This intriguing characteristic has unveiled new vistas for investigating the nature of time itself. One line of inquiry involves employing entangled particles to transmit information backwards in time. Imagine deploying an entangled particle along a hypothetical closed time-like curve in space-time, a theoretical pathway that, if traversable, permits a particle to revisit its past. If the entangled particle within this CTC could interact with its present counterpart, it could theoretically relay information into the past, potentially altering events that have already occurred. Another avenue of exploration centers on using quantum entanglement to manipulate the states of particles in the past. By leveraging the interconnectedness of entangled particles, there arises the tantalizing prospect of retroactively modifying the outcomes of past events. The concept envisions the alteration of past occurrences by exploiting the intricate relationships between entangled particles. However, it's crucial to note that these concepts remain firmly within the realm of theory and encounter substantial challenges when translating them into tangible experiments. The practical implementation of utilizing quantum entanglement to influence the past confronts numerous obstacles, including the delicate nature of entangled particles and the complex theoretical frameworks required to navigate spacetime. Yet, despite these challenges, the potential implications of quantum entanglement in influencing the past cannot be overlooked. This notion fundamentally challenges our conventional understanding of causality, the concept that every event has a cause preceding it, and opens up new pathways for exploring the nature of time and reality. The theoretical exploration of manipulating time via quantum entanglement signifies a frontier where the boundaries between past, present, and future blur, prompting deeper contemplation and reevaluation of our fundamental understanding of the fabric of the universe. The grandfather paradox and causality. Quantum entanglement, while an intriguing aspect of physics, does not facilitate physical travel through time. Instead, it hints at the potential for transmitting information or manipulating the states of particles, theoretically influencing events in the past. However, realizing these theoretical possibilities necessitates significant technological advancements to harness the power of quantum entanglement for such endeavors. It's pivotal to grasp that closed time-like curves, also known as closed time loops, constitute hypothetical pathways within space-time. These theoretical constructs propose a trajectory that, if traversable, could enable an object or information to journey back in time to revisit a previous moment. Conceptually, navigating a CTC would allow an entity to revisit an earlier point in its history, theoretically altering events that have already occurred. In the realm of general relativity and theoretical physics, CTCs emerge as solutions to Einstein's field equations, suggesting specific spacetime geometries that fold back upon themselves, potentially creating a looping effect in time. However, despite these theoretical propositions, esteemed physicist Stephen Hawking expressed skepticism regarding the actual existence of CTCs. He highlighted potential paradoxes that could arise from their existence, notably the grandfather paradox. This paradox postulates that altering events in the past could create contradictions, leading to a disruption in the time traveler's existence. Hawking formulated the chronology protection conjecture in 1992, proposing that the laws of physics fundamentally prevent the formation of CTCs to safeguard the consistency of cause and effect, thereby averting paradoxes and maintaining a coherent flow of time. This conjecture is rooted in the notion that the known laws of physics prohibit the existence of closed time-like curves. Hawking's skepticism stems from concerns about the potential violations of causality and the challenges these theoretical constructs pose to upholding a consistent and coherent universe. He argued that CTCs could disrupt the natural flow of cause and effect relationships, undermining our understanding of the fundamental laws governing the universe. This skepticism underlines the inherent difficulties and paradoxes associated with the concept of time travel, particularly concerning its impact on the foundational principles of physics. Hawking's contributions have significantly fueled ongoing debates and explorations into the feasibility and consequences of time travel within the established frameworks of physics theories. Wormholes and interstellar shortcuts. Wormholes, often the stuff of science fiction, are theoretical constructs that could serve as interstellar shortcuts, potentially connecting far-flung corners of the universe or even distinct moments in time. Picture them as cosmic tunnels, resembling shortcuts through a mountain range, allowing travelers to leap across vast distances in space-time. Initially conceived by physicist John Wheeler in 1955, wormholes emerged from the notion that by having colossal objects rotate at nearly the speed of light, their intense gravitational fields might bend space-time, establishing a bridge between two distant points. This idea is mathematically described by Einstein's theory of general relativity, a cornerstone of modern physics. However, the feasibility of these passages remains speculative, contingent upon the existence of exotic matter with negative energy density, a substance yet to be observed or produced. According to theoretical frameworks, wormholes could manifest in two forms, traversable and untraversable. The former would enable actual passage, facilitating interstellar voyages that could revolutionize our approach to cosmic exploration. Imagine reaching distant stars and galaxies by taking these cosmic shortcuts. Yet the hazards loom large. The potent gravitational forces surrounding wormholes could tear apart any object attempting to traverse them. Additionally, their instability raises concerns. These pathways might collapse unpredictably, ensnaring any unwary travelers within. The existence of wormholes, while debated among scientists, remains an object of fascination, not only in the scientific community but also in the realms of science fiction. Exploring these theoretical constructs pushes the limits of our comprehension of space-time and the vast expanse of the universe. Recent experiments worldwide offer hope, demonstrating progress in comprehending the scientific principles underlying these fantastical concepts. Although physically traveling back or forth in time remains a distant prospect, advancements in the science surrounding wormholes could pave the way for such endeavors in the future. While direct time travel might not be within our grasp, the scientific groundwork might enable our descendants to venture back and witness moments from our present era. Imagine your great-grandchildren journeying back to this current year, peering into the past to experience the world as it is today. It's a concept that stirs both curiosity and awe at the possibilities within the fabric of spacetime. So while the feasibility of traversing through time via wormholes remains speculative, the ongoing scientific exploration of these cosmic gateways tantalizes our imagination and opens doors to understanding the profound mysteries of the universe. If you could time travel, what era or historical period would you visit first? Let us know in the comments below. Thanks for watching, and we'll see you in the next one.